Okay, today we will do Fourier Series solution of endpoint value problem. EVP is a shorthand for endpoint value problem. So let me write down the equation. Say you have x double prime plus 4x equals to 8t. And let's say x of 0 equals to 0, x of 1 equals to 0. Find x such that satisfies all these conditions. Actually, you can solve this without using the Fourier series, but after showing you how to solve it using the Fourier series, I'll try to explain to you why you would want to do such a thing. Okay? So find Fourier series solution. So what we are trying to do is to find the solution of x of t in the following format. I want x of t. What's the Fourier series of x of t of any function? It's a0 over 2 plus sigma n from 1 through infinity of an cosine n pi over l t. Now because x is a function of t, I have to write it as t rather than x, plus bn sine n pi over l t. That's the kind of solution I want. And in addition to this, I want, I need to satisfy, I have to satisfy these three conditions. Okay. This one we'll think later. Let's think about these first. Okay. What kind of function will always satisfy x of 0 equals to 0 and x of 1 equals to 0? So think about a function that's like this. 0 here, 0 here. Would this be sine, right? Because if it's like that, that's like a sine curve, right? So for this one, you really want for this context, you really want sigma n from 1 through infinity of bn sine, and what's our L? Huh? 0 to 1. So L is
1.
1. So in other words, you're trying to look for a solution to this differential equation in the form of Fourier sine series. Why did we pick sine series? Because of these endpoint value conditions. Now, if your endpoint value was instead x prime of 0 equal to 0 and x prime of 1 equal to 0, you would have picked
Cosine.
the cosine ones. Okay? Because the cosines have 0 derivative at the endpoints. Right? Sine has 0 value at the endpoints. Cosine, for example, cosine function. So from 0 to L, if you have a cosine function, at the endpoints you have a horizontal tangent, so you have the derivative equal to 0 for the cosine. Okay. So depending on the endpoint condition, you're going to pick either the cosine series or sine series, and then I'll always have 0 as the left end, and if you see another condition on the right, that'll be your right endpoint. Okay, so that's what we have. Therefore, and then another thing I had to say was that now because I chose the sign, these two conditions are for free. If you plug in 0, sine of 0 is always 0, so this is always true. Right? If you plug in 1, then you get sine of n pi. What's sine of n pi?
0.
It's also, again, always 0. So these conditions are automatically satisfied. So now we only need to focus on this one. We have to see how this can be satisfied. Okay? All right, let's plug this into the left side and see what we get. If we differentiate this twice, sine differentiates to cosine, cosine differentiates to negative sine, right? So if you differentiate it twice, you're going to get negative n squared pi squared bn cosine, not negative sine n pi t. That will be the second derivative, right? That's the second derivative. Then, what is x double prime plus 4x? Well, you're taking this one and multiplying it by 4, so it'll be 4bn, add it to this one, so you end up with sigma n equals to 1 to infinity of 4 minus n squared pi squared bn sine n pi t. So that's what we get, and then I have to make this equal to 8t. Okay, how do we do that? How do we know which bn I have to use in order to set it equal to 8t? Any ideas? The idea is to make the right side look like the left side. So what should we do for the right side? I need Fourier sine series for the right side. All right, so we will have to do the Fourier sine series. Okay. All right, so right now, to do Fourier sine series of 8t, you require bn. And what's the formula? It's 2 over L, which is 1 for us, 0 to 1, of the function times sine of n pi over 1 t dt. Okay, that's what we have to compute. Let's compute this. I guess I can put so let's just integrate using tabular. So d integral plus or minus here, and then 8t, 8 and 0, sine n pi t, cosine negative n pi no, I have to integrate, so it should be negative 1 over n pi cosine n pi t, and then negative 1 over n squared pi squared sine n pi t, and then plus minus plus, and then if you read off like that, that integral is same as negative 8t over n pi cosine n pi t, okay, and then plus 1 over n squared pi squared sine, no, not 1 squared, this should be 8. So negative times 8 times negative, so it's positive 8 over n squared pi squared sine n pi t. And to this, you have to plug in the endpoints 1 and 0. And then once you do the integral, you have to multiply by 2 because 2 is in the front. Okay, so that's your Bn, and no, that's your Okay, see, I'm trying to find the Bn for this one, but there's another Bn, the Bn for xt. So I kind of made a mistake in using Bn twice. So let's put a tilde here on the top to distinguish. This is the Bn for this one, which we will later compare to this times Bn, where the Bn is for the Fourier sine series of the xt. Okay. All right. So now when you plug in 1, you get cosine n pi, which is negative 1 to the nth power. If you plug in 1 and 0 to this, this becomes 0. So in both cases, you don't get anything from here. You get something from here. And also, if you plug in 0 to this, 8 times 0 gives you nothing, right? So the only time that this produces a non-zero number is when 1 is plugged in which case you get 2 times negative 8 times 1 over n pi times cosine n pi, which is negative 1 to the nth power, which is negative 16 over n pi, negative 1 to the nth power. That's your Bn tilde. Okay? Now, what does this mean? This means that the Fourier sine series of AT is now equal to sigma n from 1 through infinity of that thing, negative 16 over n pi, negative 1 to the nth power, sine n pi t. And then you can compare both sides and conclude something, right? They both have sine n pi t. And then you have this number in front of sine n pi t, whereas on the left side you have this. So shouldn't these two equal each other? Right? If those two are equal, then the left side and the right side will be perfectly matching, and therefore you're going to have the solution. So that's what you have to do. Once you find the answer, okay, where should I erase? Let me erase the top and write down the answer. So I need 4 minus n squared pi squared Bn equal to negative 16 over n pi, negative 1 to the nth power. And then I have to solve for Bn, which means I have to divide everything by this thing. So I end up with Bn equals to negative 16 over n pi times 4 minus n squared pi squared times negative 1 to the nth power. Okay, so that's your Bn, and therefore you have your x of t. So the final answer is x of t is sigma n from 1 through infinity of negative 16 n pi 4 minus n squared pi squared, and then negative 1 to the nth power of sine n pi t. That's the solution. Okay. Any questions? All right, let me add a few more remarks. So this is, okay, so to recap what we did first we had to start from this boundary condition and say we concluded that because they're both equal to 0, we need x of t as a Fourier sine series, n equals 1 through infinity of Bn sine n pi t. That was our conclusion. And then I plugged it into the left side to generate another form that looked like a Fourier sine series. And therefore, I turned the right side, the AT, into Fourier sine series by doing this computation. After turning both sides to look like a Fourier sine series, we then just compute the coefficients and set the coefficient equal. And that can tell us what Bn is. Once you find out what Bn is, now you just plug that Bn into our original format. and then that's your solution, right? So that was how it was solved. However, this question can be solved in a much easier way if you don't use the Fourier. How do you solve it as a generic? If it was just a constant coefficient homogeneous, non-homogeneous differential equation, how do you solve that? Any ideas?
You start with R's.
Hmm?
Find your R.
Yeah. So, as a generic solution, you would do x of t. Well, first, r squared plus 4 equal to 0, so that gives you r equals to plus minus 2i. So x complementary solution is what? C1 cosine 2t, because 2. Then C2 sine 2t, okay? And you need a particular solution, right? XP should be what? You use method of undetermined coefficients. So you use something t because you have this here, so it should be AT, and then all the derivatives should be present, so if you differentiate t, you get 1. So that means you need a constant term. Okay, so this is what you need as a particular solution. If you plug this to the left side and compare it to the right side, you will find that B it should be 0 and A should be 2. Okay, you can actually, so XPT, I don't want to go into details. If you actually do this, plug this 2t on the left side, 2t times 4 is 8t, right? And 2t, if you differentiate it twice, you get 0, so this does work. And then once you have it, what do you do afterwards? You say the general solution, xt, is the sum of these two, c1 cosine 2t plus c2 sine 2t plus 2t. Right, that's the solution, is it? And then you plug in x0 equal to 0. If you plug in 0, everything is 0, so c1 becomes 0. So x0 equal to 0 gives you c1 equal to 0. Okay? And then if you plug in 1, then you get x of t, c2 sine of 2 plus 2, and that has to, x of 1, that has to equal to 0, so that gives you c2 as negative 2 over sine of 2. Okay? And then when you plug that back in, c1 is 0, c2 is this. When you plug that back in, you get x of t equal to negative 2 over sine of 2 times sine 2t plus 2t. This satisfies the differential equation and these two boundary conditions. And because of the uniqueness theory, so such a differential equation has, actually it's an endpoint value problem, so we don't know, but you can show that this has only one unique solution. And because it has only one unique solution, you know that this must be same as what? This one. Okay. So these two are the same exact solutions. So what's going to happen is that if you actually took this and found its Fourier series, if you find the Fourier sine series of this thing, it's going to match exactly to this one. Okay, so that's what you're going to find. So that's another very messy calculation. So I don't want to show it to you, but this solution and that solution would be equal. Okay. All right. So that kind of brings into question of why would you do this when you can do this? Well, and that's actually perfectly good argument. You want to do it this way, not that way. So this is not used that much, but this one reason that we do it is because it can show you how Fourier series can be used to solve differential equations, and it gives you something to think about before going into partial differential equations. Another thing is, we know that you can only do this, you can only find the Fourier sine or cosine. No. You can only find the method of undetermined coefficient solutions by if you have something easy, right? So in case when you have something like the absolute value function or some piecewise function, those things you can't solve using method of undetermined coefficients. However, you can find their Fourier series. That's possible. Right? So there are cases where the right side is a function where you can't handle with the method of undetermined coefficients, and therefore, for that case, you really need to use the Fourier series solution. So that's why we're doing it. But you know, when we have to deal with the piecewise, that's even harder. So that's why I avoided it. Yeah. So that's why we did the simpler one. But this is good enough example to show us how you can solve a differential equation using Fourier series.